Biology is really simple. Everything in biology works based on a few basic principles. The action potential is a really good example of this. It might look really complicated, but all you need to know is how diffusion and active transport moves ions. This is the structure of a myelinated neuron, and if we look closer at the axon, we can see that when the neuron is at rest, there is a higher concentration of sodium ions outside the cell compared with the concentration inside, and it's vice versa for potassium. Because of the concentration gradient, an active process is needed to maintain this situation, the sodium-potassium pump. This uses energy in the form of ATP to move the ions against their diffusion gradient. And this gives us a resting potential in the neuron, which is about minus 70 millivolts, and it's said to be polarized. Now we're going to look at what causes the pattern of changes in membrane potential when the neuron fires. Looking at the soma of the neuron, we can see the dendrites. This is the site of synapses with neighbouring neurons. The impulses received are processed, and small amounts of depolarization spread to the axon hillock. If this small amount of depolarization reaches a threshold, it causes voltage-dependent sodium channels in the axon membrane to open. Sodium ions diffuse along their concentration gradient into the cell, causing the inside of the neuron to become positive compared to the outside. This stage is represented in the uphill part of the action potential trace. The depolarization from the soma reaches threshold and opens the sodium channels, and this allows a rapid influx of sodium ions. This stage of the action potential is called depolarization. Looking back at our neuron, the sodium channels now close, and potassium channels will allow potassium ions to diffuse out of the cell. This swaps the polarity of the membrane again, so that the inside is now more negative than the outside. And we can see on the graph that depolarization generally reaches around plus 40 millivolts before these potassium channels open. As potassium ions diffuse out, this causes repolarization of the membrane as the inside becomes more negative again. Potassium channels open and close very slowly, meaning that too much potassium diffuses out, resulting in hyperpolarization. This is then corrected because sodium and potassium leak through the membrane. This is by diffusion with their concentration gradient. The sodium-potassium pump also helps. This brings the membrane potential back up to the resting potential. And you can see this in the graph too. In the final part, potassium channels close and the hyperpolarization is corrected. This restores the resting potential. The time when the membrane is hyperpolarized is called the refractory period, and during this time no action potential can occur. And this also means that the action potential always travels in only one direction. Remember, we have been looking at only a small section of the axon. The nerve impulse is propagated because these events occur repeatedly next to one another. The depolarization during the early phase of the action potential travels along the next part of the axon. This opens voltage-dependent sodium channels, and the process repeats. This is how the impulse is passed along the length of the axon. Remember also that in a myelinated neuron, like the one pictured here, action potentials only occur in the nodes of Ranvier. These are areas where there's no myelin insulating the nerve, and it produces faster conduction, as the impulse can jump from one node to the next. The action potential is really simple. All you need to understand is diffusion.